Hello, my name is Sad Lalali, and today I'm excited to present our work on cross-modal distillation for 2D and 3D object discovery from 2D motion. We are pleased to share this work for CBVPR 2025. Let's start with the why. 3D scene understanding is crucial for many applications like autonomous driving. However, acquiring labeled 3D data is incredibly expensive and time-consuming. Annotating a sized scene can take hours, up to 4.5 hours for complex residential areas. Furthermore, the real world isn't static. New objects and categories appear constantly. We need systems that can adapt and learn about these novel objects without relying on exhaustive pre-labeled datasets. This is where object discovery comes in, the ability to identify and learn new objects without explicit supervision. So how can we discover objects without explicit labels? One powerful cue is motion. Objects that move tend to stand out from their static background. While 3D motion data exists in the form of scene flow, its 2D equivalent, which is 2D optical flow, which is derived from standard camera image videos, provides much denser information across the scene. This density is key. Our plan is to leverage mature 2D object discovery techniques. One fundamental concept is a slot attention mechanism. Think of a slot as a container that learns to bind to a specific object or region in an image, enabling unsupervised object discovery and segmentation. In the work by Kara, presented at WICV 24, supervision with motion masks guides the model to focus its slots on moving objects, and then these slots generalize to static objects. Further advancing to the object discovery, the joint paper presented by Kara at CVPR 24 introduced the self-distillation scheme. Here, a student and a teacher model process strongly and weakly augmented versions of the input sequence. The aim is to enrich the student's attention by transferring knowledge from the teacher, specifically by retrieving objects activated in the teacher's attention while filtering out noisy segments using the teacher's confidence. Now our goal is to extend these successful 2D object discovery principles to the 3D domain. A straightforward approach might be to take a 3D punch cloud, project it into a front view 2D representation, and then apply the existing 2D object discovery pipelines, like for JUD. However, this represents a significant challenge: sparsity. As you can see from the images, a front view projection of a LiDAR punch cloud is very sparse. In fact, only about 18% of the pixels present in the projection typically have an associated 3D punch. This sparsity makes it difficult for models to train on dense RGB images to perform effectively. To address these challenges and adapt 3D motion cues for 3D supervision discovery, we introduce our first baseline, JUD 3D. This method incorporates several key ideas. First, the motion mask filtering. We refine the 2D motion mask by removing noisy areas that don't have corresponding 2D 3D points. Then, scene completion. Crucially, we imply a scene completion module. This predicts a dense punch cloud from the sparse input, which significantly improves the quality of subsequent segmentation. Then, intramodal distillation. Similar to JUD, we use a teacher-student setup within the 3D domain. The teacher model refines the student's object's mask based on its confidence. The slide visually demonstrates the impact of scene completion. On the left, you can see the sparse front view projection of the punch cloud, which is given as input. On the right, the output after our scene completion module, which is much denser and much more amenable to 3D object discovery. The associated RGB image is shown for context. We evaluate on the KITTI and 3PD datasets using metrics such as F1 score. To 3D, our 3D adaptation shows promising results. For instance, each performed on 3PD, it achieves an F1 score of 39.6 in 3D. While So 3D is a good starting point. We can do better by explicitly leveraging information from both 2D and 3D modalities. This leads us to our main contribution, xMOD, a cross-modal distillation approach. The core idea is mutual learning between 2D RGB images and 3D point cloud projections for object discovery. We use a dual teacher-student system with parallel networks processing 2D and 3D data streams. Then cross-modal supervision is key. We leverage the dense 2D motion cues to guide and improve 3D learning, and conversely, 3D spatial information helps enrich the 2D understanding. Also, modality-specific regularization using motion mask guides learning within each domain for 3D and 3D. And we continue with project task with 2D image reconstruction and 3D scene completion to enhance feature representation in both modalities. The benefits of this cross-modal learning are evident in the results. Looking at the table, our xMOD 3D method, which benefits from 3D guidance, improves the F1 score by 3.6 points on KITTI compared to the original 3D JOD. Similarly, xMOD 3D guided by 2D information achieves 3.4 points F1 score improvement on KITTI compared to the JOD 3D baseline. However, each modality also introduces its own types of noise and inaccuracies. This slide shows some qualitative examples. You can see that while cross-modal learning helps, some modality-specific artifacts or missegmentation can still occur. Further improve reliability and filter our modality-specific noise, we introduce a late fusion strategy at inference time, when both RGB and LiDAR data are available. The idea is to leverage multimodal agreement using the intersection of a union criteria to keep only most confident segments. By discarding inconsistent modality-specific predictions, we filter noise and increase the confidence of our model. The quantitative impact of this late fusion is significant. Compared to xMOD 2D alone, the fused xMOD 2D plus 3D improves the F1 score on KITTI by another 5.3 points, reaching 27.4. Finally, it's important to acknowledge the current limitations of our method. The table here shows performance broken down by the distance of objects from the sensor on the KITTI dataset. We observe lower performance for objects that are either too close, 0 to 10 meters, or too far, 30 or to 70 meters. The method performs best for objects at mid-range between 10 and 30 meters. This is likely due to the fact that objects are often truncated when they are very close to the sensor, or due to the sparsity of point clouds for very distant objects. The average number of points per object clearly decreases with distance, highlighting this challenge.